Key terminology in Bronsted-Lowry acid-base theory. Acid and its conjugate base. A base and its conjugate acid. The difference between the pairs is one hydrogen ion. So here is an example. Acid gives the conjugate base by taking away one H plus ion. HCl becomes Cl minus as a conjugate base. H2Se becomes HSE minus. HClO becomes ClO minus. And H2SO4 becomes HSO4 minus. Notice that this is the loss of one H plus ion. The base and its conjugate acid, there's a gain in one H plus ion. So for example, CO32 minus, the carbonate ion, gains one H plus ion to become hydrogen carbonate, HCO3 minus. Notice that the gain is in one H plus ion. There is an increase in charge from -2 to -1. Strengths of acids. Strong acids dissociates. It is also called ionize 100% to the conjugate base, which is a very weak base from a strong acid. For example, hydrochloric acid HCl ionize to H plus and the chloride ion. Sulfuric acid H2SO4 ionize to H plus and the hydrogen sulfate ion. All physical states are aqueous. An alternative and equivalent chemical equation for the two above is by adding water as part of the equation. So for example, HCl plus water gives H3O plus, called a hydronium ion, and chloride ion. H2SO4 plus water gives the hydronium ion plus hydrogen sulfate ion. This means that the hydrogen ion, H plus, is exactly the same as the hydronium ion. Strong acids give weak conjugate bases. It is important to remember some of the strong acids. The strong binary acids are HCl, HBr, and HI. Strong oxyacids are sulfuric acid, nitric acid, and perchloric acid. These are all inorganic acids. Stabilization of the resulting conjugate base leads to strong acids. The more stabilized the base, the stronger the acid. There are several factors, but for now, the two most important ones are electronegativity and atomic size. The trend in acid strength for binary acids. In assessing the strength of an acid, we look at how its conjugate base is stabilized. For example, let's look at the second row binary acids. From left to right of the periodic table, carbon, nitrogen, oxygen, fluorine, CH4, NH3, H2O, and HF are the acids. Each substance can potentially serve as an acid as they have proton to donate. So, we first assess its conjugate base. Given here, CH3 minus, NH2 minus, OH minus, and F minus, and ask the question, what is stabilizing the negative charge? For these examples, the electronegativity is stabilizing the negative charge. Recall, the electronegativity is the ability of an atom to pull electrons to itself. Please review the video on covalent bonds. Fluorine is the most electronegative element, followed by oxygen, followed by nitrogen, and then carbon. The acid strength therefore increases from left to right, with HF, hydrofluoric acid, is the strongest acid in this list. Trends in acid strength for binary acids continue. From the previous slide, periodic trend from left to right along a row from boron to fluorine was due to electronegativity. The periodic trend down a column from fluorine to iodine, or from oxygen to tellurium, is due to the ionic size. Here in this figure are the acids from group 17, from hydrofluoric acid to hydroiodic acid. Hydroiodic acid is the strongest acid because after assessing its conjugate base, I- is the largest ion, which stabilizes the negative charge better because the charge is spread out more in a bigger ion.